Hello everyone, welcome back. So now we're in example 2. Yes, example 2. So what does it say? Well, it says the cross-section of a composite beam that consists of 3 millimeter thick fiberglass faces bonded to a 20 millimeter thick particle board core is shown in that figure. Now the beam is subjected to a bending moment of 35 newton meters acting about the z-axis. And the elastic moduli for the fiberglass and the particle board are 30 gigapascals and 10 gigapascals respectively. Okay, so what do we want to know? Well, we want to know the maximum bending stresses in the fiberglass faces and the particle board core, and the stress in the fiberglass at the joint where the two materials are bonded together. So right there. Okay, now, I know this is the whole transform section method. We didn't quite do that last time, but I'm going to go ahead and let you try this on your own. I believe in you. I think you can do this. If you can't, I was wrong. I'm sorry. But go ahead, pause, try it on your own, see if you can do it. If you can't, that's completely fine. Come on back, and we'll do it together. So 3, 2, 1, you've paused, you came back, and hopefully it went well. We're going to find out. So let's do it. Now, for this, we're going to say the particle board, the center one, is material 1, and the fiberglass on the outside is material 2. Now, we can get the modular ratio by looking at their modulusicity. So, fiberglass over particle board. So it's going to be equal to 3. Now, we're going to transform the fiberglass faces into an equivalent amount of particle board by multiplying their width by the modular ratio. So they get wider. They were 50 millimeters, now they're going to be 150 millimeters. So now we're replacing those two fiberglass faces by a 150 millimeter wide and 3 millimeter thick particle board face. So it is absolutely bonkers looking now. It's like something like this. Crazy. Okay. Now what's the moment inertia going to be for this new crazy section? Well, we have to figure out what the moment inertia is for the transformed fiberglass faces, as well as the particle board core. Now the centroid is pretty easy. It's symmetric. So we know the centroid is just right there at the center. We don't have to do any calculations there. We also therefore know that the particle board core, well, it's right on the centroid. Its centroid is the centroid, and so none of that parallaxis theorem for it. Our transformed fiberglass sections, though, they're going to need some corrections. So first, we know it's going to be 1/12 base times height cubed for them. Base times height cubed. Don't have much height though, because they're 3 millimeters thick, so it's a fairly small number. However, their new area, their transformed area, is going to be equal to 150 times 3, and they are a considerable distance away from the centroid, from their center to that center. So with that, d squared a, we actually have a fairly large component of moment inertia from the parallel axis theorem. So that correction term really does mean that they are very considerable. So we get our moment inertia about the z-axis is 153,033 millimeters to the fourth. Okay, now what's the bending stress in the particle board core? Well, from the flexure formula, we know it's always going to be at a maximum at either the top or the bottom of the board. And so that's going to be equal to 2.29 megapascals, which is pretty easy. Nothing too terrible there. Now what about that bending stress in the fiberglass faces? Well, just like with the particle board core, it's going to be at the outer limit there. Be very careful though, that value y, that's from the neutral axis. Not just like the neutral or the centroid of my particle board, sorry, of my fiberglass face, but actually of the whole composite material. So it wouldn't be 1.5 there, it's actually 13. Going from the center all the way to the edge. And so we calculate it, and then we multiply it by our modular ratio to get the answer. And we get this to be 8.92 megapascals. If you're wondering where the negative sign goes, we just don't care because I'm only asking you for the maximums. So I could have done negative times a negative. I'm just choosing one at random. If I'd asked for the maximum tensile, I don't have to worry about that. Okay, now what about that shear force? Sorry, shear bending stress at that interface. Well, at that interface, we know that we've gone up 10 millimeters, and it's going to be the exact same as for our previous one. However, you might be wondering, well, what's going on here? Wait a second. Wait a minute. Whoa. Looking back here, like it was 2.29 before, and that was 10. And now, all of a sudden, we're getting this one, and it's 6.86. What happened? Modular ratio. Don't forget that. I have jumped the barrier. There's a discontinuity in my shear stress diagram. Looks something like this, and then suddenly it jumps because we have that transformed section. So on this side, in the particle board core, it's 2.29. And then we suddenly jump up in the fiberglass section, it's 6.86. Okay, so is that discontinuity? Whoop. So that is it for this time. That is it. So thank you very much for listening. I hope this helps you, and I hope this makes sense. Just remember that this jump here is because of that discontinuity caused by our transformed section, okay? So don't let that get you too confused. Transform. Thank you for listening. I'll see you all next time. Have an absolutely wonderful day. Bye-bye.